Okay, now we want to talk about how much heat is it going to take in order to change the state of material. This is going to be the amount of energy it's going to take to break those springs. So let's go back to our formula for how much heat is stored in a material, and that's this formula here. So you notice it depended on what the material was, so that was a specific constant for the material. So steel would have a certain specific heat constant, and then water ice would have a different one. And then it depended on the amount of material that you had, so that a larger object could store more heat. And then it also depended on the change in temperature. So if the temperature changes by quite a bit, then that means a lot of heat had to be transferred to that material in order to do that. So our formula for how much heat does it take to break those bonds and change the state of material is going to be Q, and then there's a different constant. So this constant is different than this constant up here, and I'm just going to put a triangle. But to be more specific, you would say change of state. And there would be one constant to change from a solid to a liquid, and then there would be another constant in order to change from a liquid to a gas. And then there's a different constant for every kind of substance than you can think of. Then it's also going to depend on the amount of substance. So if you've got a big ice cube, it's going to take a lot of heat in order to melt it. If you got a little ice cube, it doesn't take so much heat. So it also depends on mass, but you notice that there's nothing over here about T. Now, it does occur at a specific temperature. So, for example, water ice changes to liquid ice at 100 degrees Celsius under 1 atmosphere of pressure. And then, if you want to change liquid water into gaseous water, steam, then you have to elevate the temperature up to 100 degrees Celsius. But as long as the material is changing its state, so as long as it's changing from ice into a liquid, that occurs at one temperature, and then that temperature does not change until it's completely melted. And then once it's completely melted, then its temperature starts to go up according to this formula up here. So we'll talk more about that later. All right, so here is a chart of latent heats, or in other words, this thing right here. So those are those latent heat constants. And it goes by different words. So in this chart, they refer to it as latent heat of fusion, which is melting, and then the latent heat of evaporation, which is changing from a liquid to a gas. So we've got two sets of constants here. One, if you're going from the solid to the liquid, and then the second set of constants is if you're going from the liquid to the gas. And then also it shows at what temperature will this occur at. So let's use this formula here. So how much heat does it take to melt 20 grams of ice? So we're going to write down what we're given and what we're looking for. The mass is 20 grams, but that's the wrong unit. Because if you go up here, you'll notice that these C values have kilograms in them. So that means that we need to change it from grams to kilograms. We're looking for the amount of heat. So the equation's pretty simple. We only have two things that we need to multiply here. So we multiply those two things together, and then we get 6,700 joules of heat is going to be required to melt that material. So what about if you had twice the amount of mass? So if there was 40 grams, how much heat would it take? So if you have 2 times the M, it's going to be 2 times the Q. So then that's going to be something like, 1,300 and 400, whatever that is, 13,400 joules. Okay, let's try this. We also want to talk about the sign convention, so that when you go from a solid to a liquid, it's going to take a certain amount of heat. So that's going to be positive Q. You have to put heat into the system in order to go from here to here. But what about if you're starting with a liquid and then you're going to a solid? What would you do? So if you're going in the opposite direction, that's going to give off heat. So this water will give off heat as it turns into ice. And so this is going to be minus Q. So we're going to, and then we can do the same thing over here. If we want to go from a water and turn it into a gas, then we're going to have to add heat to it, so positive Q. And then if we start with this and then we go back to water, then it's going to give off heat. Now, how do you know that that's true? Well, have you ever played with a vaporizer? So a vaporizer is one of these things that you put the water in it, you plug it into the wall, and then it starts giving off steam. And so you might have tested to find out if there's any steam coming out of the vaporizer by putting your hand down there, and then, ooh, you just burned yourself. So why is that true? Now, you can't see the stuff coming out of the vaporizer because it's a gas. Now, when you start to see the fog or the cloud that's coming out of the vaporizer, that is when it's changed into a liquid. So you only see the water when it is in a liquid form. It's the same thing with a cloud. So the only reason why you're seeing a cloud is because the water vapor, a gas, has condensed into water droplets. And so in order to do that, heat is given off. Where do you think that heat goes? That heat goes into your hand when you put it on the vaporizer. And the sensation of heat entering your skin is hot. And the sensation of heat leaving your skin is going to be cold. So that's the reason why you burn yourself. And whenever water changes into a liquid, it gives off a tremendous amount of energy. So a steam burn can actually be worse than taking your hand and putting it into boiling water. Don't do either one of them, okay? But just want you to know about that. And then also notice we could continue to go over here to plasma. And so that if you start with a gas and you get rid of those electrons, that's going to take heat. So again, positive heat. And then if it changes, it deionizes and goes from a plasma back into a gas, that's going to give off heat. Okay, let's take a break, and when we come back, we will discuss graphing heat versus temperature in these different kinds of changes.